Hey everybody, it's Steve, and I've got some power supplies to show you today. Now I want to make a quick public service announcement about power supplies. Stop buying fake power supplies from eBay, Amazon, AliExpress, Walmart.com, pretty much every online source. Stop buying them. They're contaminating the supply chain, and it's becoming harder and harder to tell which power supplies are genuine and meet the ratings that are listed on the labels on the back of the supply, and which ones are fake and counterfeit. I would even go as far to say to stop buying power supplies from online sources unless the seller gives you some kind of a warranty or a money-back guarantee, effectively that protects you in case you get screwed like I did. So have a quick look at these 4 power supplies and try to guess which ones are real, which ones are fake or counterfeit, which ones work, which ones don't. I've already opened many of them up, so you might see some dings on the side. Don't let that throw you off. Now, while you're thinking about that, I should define what I mean by a fake power supply. Basically, it's any power supply that does not meet the standards that is listed on the back of its label. And in my case, I'm basically looking to make sure that the output is indeed truly what is written on the back. Let me explain this a little bit further. These are all switching power supplies, switch mode power supplies, and they're regulated power supplies. I'm going to show you this one here as an example. If we look at the label on the back of the power supply, it has a range of voltages that it will take as the input. In this case, it's a universal mains voltage, 100 to 240 volts, and it will output 12 volts at 2 amps. So it doesn't matter what the input voltage is, as long as it's in this range, it will always put out 12 volts, as long as you're requesting 2 amps or less. So if my device is consuming 1 amp, it'll put out 12 volts. If it's consuming 100 milliamps, it'll put out 12 volts. If it's consuming 2 amps, it will put out 12 volts. You get the idea. However, if I go beyond the 2 amps, then the behavior is undefined. In most cases, it'll just cut off and it will shut down. Let's take a look at these ratings and let's see if that will give you a clue as to which one is fake and which one is not. So just like the first one we saw, this one also has a universal mains input and it also puts out 12 volts when you request up to 2 amps. The next one is a little bit bigger. It is a Lenovo power supply. And if we look very carefully, we'll see again, universal mains input, and it puts out 4.5 amps at 20 volts. Finally, we have this power supply, and it is putting out 24 volts at most 3 amps, again, universal mains input. And I should note that all of these are made in China as well. So have you figured it out? Which ones are real and which ones are fake? And therein lies the problem. How could you possibly know without testing these things in advance? You have to rely on the seller's word. You have to rely on the reviews being genuine. You have to rely on somebody actually buying it and doing the test and reporting back the results. So if you haven't figured out which ones are real and which ones are fake, I'll tell you that this guy is real. I think this one was pretty obvious. It is a genuine Lenovo laptop power supply. This guy is pretty good. No problems with this one. What about the other 3? Well, this one here is a close second place to being genuine. It has a really tiny problem, but for what I use it for, it's okay. These 2 guys, absolute garbage, pure trash. And I'll show you how they failed in just a few minutes. Okay, you've just bought one of these cheap power supplies on eBay, you got it for a great deal, and now you're wondering, uh-oh, how do I know whether it's fake or not? All the reviews seem to imply that it was pretty good. Well, let's take a look at some things you can do to identify fake power supplies once you get them at home. Now, the obvious test to do is to basically hook one of these things up and try to draw the 2 amps at 12 volts or the 4.5 amps at 20 volts from your specialized lab equipment. Do you have specialized lab equipment? Do you have a programmable load to do that type of work? Probably not. And I think that's what a lot of these guys that are creating these fake supplies are banking on, that once it gets to your house, it's either going to work for a short period of time, or maybe you're just not going to notice that it's not actually running at the rating that's on the back of the label. So apart from not having a programmable load, how else can we determine whether these things are good or not? Let's take a look at 3 different ways. I'm going to focus on these 2 to begin with. The first thing you can do is compare the power supply that you purchased to one that you already have, if it's similar. So in this case, they're both 12 volt 2 amp supplies, so I expect them to be similar in characteristics just by observation. And if I look at this, I can tell that the one on the right is a little bit bigger than the one on the left. It's not much bigger, but it's fairly noticeable. So that's a little strange, but maybe that's okay. So I have my scale, and I'm going to weigh both of these supplies just to see if there's anything obvious that I can infer from their weight. Let's take a look at the good one to begin with. And I'm going to do this without the power cord since that's not important. And that weighs about 106 grams. Okay, let's take a look at the fake supply. And that only weighs 49 grams, which is half of the weight of the other one, roughly. Now that's too much variance in the weight there. I would have expected these to be a lot closer in weight since they produce the same output. Okay, let's take a look at the other 2 power supplies and compare them. So it's not fair to compare the weight of these 2 supplies since they produce different outputs. This is a 90 watt supply, 20 volts at 4.5 amps, and this is only 72 or 73, 24 volts at 3 amps. But what I can tell by looking at these is that this one is bigger than the one on the left. When I put them next to each other, you can see that one is a little bit wider. They're about the same length. And in terms of the thickness, the one on the right is a little bit fatter as well. So what can we infer about the size difference? Well, in general, if the rating of a power supply is higher than the other one in terms of its output watts, or maybe even its current, you would expect the one with the higher power output to be larger than the one with the smaller power output. This is a general rule. It's not something that's going to apply universally. There are some exceptions to it. But the reason why that expectation generally holds is that if you draw more current, you expect the components in the device to be larger. Transformers are going to be larger, diodes are going to be larger, and transistors are going to be larger in general. And because those things are larger, they have to sink more current, they have to sink more heat. There's often going to be a heat sink attached to it to dissipate the heat that they consume more efficiently. Smaller components don't consume as much heat, they don't need the heat sink. And as a result of that, those things are going to take up more space. So in this case, it's very unusual that the larger power supply is the one with the lower power rating. Again, not a rule, but just something to keep an eye out for. The next thing you can check is how easy it is to open these things up to get at the components that are inside. In the case of the Lenovo enclosure, it wasn't too simple. The case was glued and I had to get creative with a hammer and screwdriver to break the glue seal before I could open it up. Not so much for this guy. In general, you do want these power adapters and power supplies to be sealed. And I know it's a deterrent from the engineers and from the tinkerers that want to explore what these things are made of, but from a safety perspective, it's actually a good idea. These are mains voltage power adapters, and universal mains for that matter. So in the worst case, you've got 240 volts coming in here. If you crack this thing open and start tinkering around in there while it's plugged in, you're in for a nasty surprise, maybe even a fatal one in the worst case. I know most of us are intelligent enough not to do that, but from a designer's perspective, it's a good idea because you can't assume on the intelligence of your end users. So in the case of this power supply, I was able to get a spudging tool and wedge it in and kind of pop off the clips that are all around the external perimeter of this supply. And once you do that, then you can just crack the thing open and it comes apart fairly easily to expose its internals. A similar case for the other two power supplies. This one is glued shut. There was no way I can get my spudging tool to break the seal on the outside. In fact, I want to keep it this way because I don't plan on tampering with this. But this guy, it's pretty easy to break into. Let's see if I can demonstrate that. And we're in. Okay? Done. Finally, the last thing you can do is you can take a look at the circuit board, or basically what you find inside one of these things after you open it. Let's take a look at this one first. Once inside the power supply, I tend to take a look at the circuit board and its enclosure for anything that just looks out of place. And the first thing I see is that there's a lot of unused space in this enclosure. In fact, there are these foam pieces that are stuck onto the top of this transformer and to the back of the circuit board. And presumably this is intended to stick the circuit board in place and not have it rattle around, tipping you off to something being awry on the inside. Now, I'm not going to pretend to understand what all of these components do in this topology of the circuit board, but what I do see is that there are some unpopulated components or unpopulated footprints for the live and neutral connections to the mains. And when we look on the back, we'll see that the wires, they're just soldered onto the back of the pads. This might be okay, but these wires do look a little bit thin and flimsy for mains voltage and current applications. And next we have these two holes in the circuit board, which typically are used to mount the circuit board. You would often find some pegs or maybe even some standoffs where you could screw the circuit board and mount it in place, but there's no indication of that in this enclosure at all. In fact, what's really telling of a bad design here is the isolation between the main side of the power supply and the low voltage DC side of the power supply. The isolation is basically what protects you from being in contact with mains voltage should anything go wrong. And it's basically this gap right here. So this is okay. It's about a centimeter in width, but as you follow it up the circuit board, it all of a sudden gets pinched off right about there. And that's maybe about 2 millimeters wide. And it's really unnecessary because of this mounting hole. If this mounting hole were removed, because it's not really needed for this enclosure, then this trace could get shifted over and this component could get mounted in such a way that this isolation is maintained throughout the circuit board and the power supply in general. So everything here that I can see indicates that this circuit board was actually designed to be used in some other application, and they just took it and maybe salvaged it and put it in this larger case and sold it off as a more potent power supply than what it actually is. Now, if you want to learn a lot more about how the topology of these power supplies are designed and how they generally fail and all the different shortcuts that people take when scavenging and repurposing these supplies, I'm going to recommend that you go and look at the Diode Gone Wild channel from Dan in the Czech Republic. That guy has a whole library of this type of analysis. He intentionally buys these types of cheap power supplies from all the various online sources with the intention of trying to get them to fail, taking them apart, analyzing them, figuring out what shortcuts are made, etc., etc. There's a whole wealth of technical information over there. Go check out his channel. It's pretty good. Here's the other phony power supply. Again, it's put in a case with this rubber foam to prevent it from bouncing around. And there's ample space inside this power supply to house this and its raised or larger components. So let's take a look at the board. The board looks okay. The first thing I see is there's a bit of residue all over this board. Maybe it's flux, maybe it's something that was used to clean it. I don't know, but it certainly hasn't been tidied up. All this brown stuff is pretty much everywhere across the surface of this board. And there's an unpopulated footprint for another one of these diodes. Now, I don't know if this diode was intentionally removed to reduce the costs of manufacturing for this board, or maybe this board is used in other applications and they just didn't need it in this particular version. The AC power connector is a bit odd. It is a 3-pronged power connector, but only 2 of the prongs are actually being used. When we look on the bottom of the circuit board, the live and the neutral is connected to other parts of the circuit. Here and here, I think this is the fuse, and the ground is not connected to anything. It just stops right there. So that's a little unusual. I mean, there isn't anything metal that we would be touching on this case, so grounding really isn't needed. But at the same time, why didn't they just use a 2-prong outlet, just like all the other power supplies do? Bizarre. The isolation looks pretty good. It's about 2 to 3 centimeters wide, almost an inch, and it gets pinched at the top over here, but I think that's okay because of the components that are used to bridge this gap. So I think this power supply is actually genuine, but this is going to be a good segue to talk about how it failed. Take a look at this picture. Both of these capacitors on the output, the green ones, exploded one day while I was using it with my temperature-controlled soldering iron. I was probably drawing the maximum current that this power supply could provide, and then I heard a bang followed by a sizzling sound, and I immediately knew some of the caps inside had burst. So what I did was I replaced these 2 capacitors with higher voltage rated capacitors. I thought they might have been dried out, or maybe they're a little old, or just maybe they weren't rated properly for the voltage it was putting out. And that was a little bit premature, I think. I should have done a bit more analysis to see what caused these capacitors to fail, because as soon as I put these 2 new ones back in place and I plugged things in again, then they started to sizzle again. They didn't explode because they were actually taking the voltage that came out quite nicely. So I tested the voltage and it was over 50 volts. Which was surprising. It's only supposed to put out 24 volts. These capacitors are rated at 50 volts, so they're pretty much done, I think. But I should have been a bit more testing to see why the voltage was 50 and not 24 on the output. So I tested this diode, they were fine. Tested the transistor, it's fine. Tested this diode, it was fine. Bridge rectifier was fine. Everything looked good. But what I failed to see was this guy on the back of the circuit board. There's a tiny little diode here that is all black and it's melted. We'll see if I can get this into focus. There we go. And I didn't notice that diode and I didn't test it. And what most likely happened was that this diode was not rated for 3 amps of current. They probably used an inexpensive component, didn't check the rating, and when I loaded it for too long of a time, it just went kaboom. And that caused a side effect, which ultimately led to a higher voltage being put on the output, and the capacitors failed next. They exploded because the voltage was higher than what they were rated for. So this was okay. This power supply could have been good, but there were some shortcuts taken in its implementation. In its assembly, they used some improper components, and that ultimately led to its failure. Very quickly, let me show you what a proper power supply looks like when it's made by a well-known company. This is the Lenovo laptop power supply, and it's surprisingly different from everything else we've opened up so far. The component, this brick that comes out, is very well packed inside of this case. There's no extra room for it to wiggle around, and there's nothing in there that's propping it up to prevent it from wiggling around. It's pretty well packed in there. All this metal that we see on the outside looks like it's both a heat shield, or a heat sink, I should say, and an RF shield at the same time. So any electrical noise that's produced by the atmosphere may not interfere with this device. And at the same time, any electrical noise that it produces may get dampened by this shielding on the outside. I haven't been able to open this up, quite embarrassingly, because that other power supply I was showing you, this guy right here, was the source for my high temperature soldering iron. And when this failed, that means I can't use my high temperature soldering iron, and I can't get at this tiny little solder joint over here because it's basically being heat sinked by this entire piece of metal. So even with my crappy 30-watt soldering iron, there's no way I can undo this. I really do need a lot more heat. And I did want to show this, but unfortunately I can't. But What I can show is that there is some well thought out design in this power supply. This coil that we see on the input is effectively there to suppress any ripples or any noise that comes in on the current. So you know that the power supply is supposed to regulate the output voltage. Well, that doesn't do anything for the current. You have to try and clean that signal up as well too. So any spikes or any noise in the current will get choked, and this is what most people call this a choke, by this component, which is really nice. You get a nice clean signal on the inside of this supply. And on the output, let's see if you can see that, there's also another choke on the output as well. So the signal coming out is also filtered as well, which is great. And I suspect that if we open up this supply, we'll see a lot more components. It won't be as sparsely populated as this guy, and it will just have a better design in general. This supply over here, no chokes on the input, no chokes on the output. Very economical. Finally, let's demonstrate what happens with these two power supplies when we put them under load, specifically a load that approaches their maximum output rating. Now, initially I had mentioned that you should use a programmable load to test these supplies under ideal situations. And that way you can set exactly the current and exactly the voltage that you want to put out to stress these devices. So if I don't have a programmable load, what could I use? Well, I have this hard drive and its circuitry that would fit for its external enclosure. This hard drive will draw at least 1 amp of current. You'll see that the hard drive itself will put out, or will draw 900 milliamps at 12 volts. And I don't have a rating for the circuit, but that's typically going to be on the order of a couple hundred milliamps since there aren't any moving parts in here. So what should I expect to see if this device draws more than 2 amps of current on either of these power supplies? Well, we would expect the voltage to go down. It wouldn't be able to sustain the 12 volts at a higher draw than 2 amps. And the reason for that is because we define power as voltage times current. So the power rating of these power supplies is specifically the voltage that it can put out multiplied by the maximum current. They're both 12 volt, 2 amp supplies, so the maximum power that they can put out is 24 watts. If I try to draw, say, 3 amps at 12 volts, then I would be creating power because 12 times 3 is 36, and that's just not physically possible. So to compensate for that additional draw, the voltage must come down. It has to come down to 8 volts to maintain the equality of the equations. 3 times 8 is 24 watts, and that should be okay. This device can't operate at 8 volts, so it would just shut off. And that's why I mentioned earlier that usually the failure of these things is that they will not power up the device that you're trying to operate if they're not actually designed to put out the 2 amps or the voltage that's rated on the back of the power supply. So first thing we'll do is we'll hook up the sort of good power supply and see what it does, and then we'll compare the results with the next one. I'm plugging this thing in. I'm going to plug in the lead down here, and let's put my multimeter on voltage mode, and let's check to see what the device is, or what the power supply is producing right now. Okay, it's producing 12 volts. I will power cycle the hard drive and watch what happens when it starts up. Okay, so there was some fluctuation in the voltage there. And I don't know if you heard the hard drive spinning up, but the voltage fluctuated specifically when that hard drive was spinning. And this hard drive will consume its peak current when the motor is spinning the thing around, right? Moving parts generally require more power to operate than static parts. So if we assume that this thing draws at least 1 amp, let's say 1.5 amps, then the power supply I have plugged in right now is kind of struggling when this device spins. And so it's not really rated for 2 amps. It might be, but the voltage would probably drop below 11 volts, maybe around 11 volts at that level. And who knows, maybe this device would cut out if it ever approached that. Now, I also know that this power supply, I'm going to unplug it, struggles a bit because I use it to power my Raspberry Pi. And I use that to power it through a voltage regulator. Now, the Raspberry Pi is an interesting little computer in that it will self-regulate itself when it's not getting the voltage it needs to operate. So it will throttle its CPU down to a slower speed, and you will notice that. You'll get an indication in certain pieces of software. And that happens almost all the time when I max that thing out. So this guy is kind of okay. He's pretty close to 2 amps, but I don't think it's exactly 2 amps. I think it's probably 1.5 or maybe somewhere around that area. All right, let's do the same test with this crappy supply. And I know for certain this thing just does not work. And let me demonstrate that. First we'll plug it in. Turn the circuit off. Okay, that's plugged in. Let's measure the voltage it's putting out without any load connected to it. And it's a little over 12 volts. Okay, and watch what happens when we turn this on. Kaput. It drops well below 10 volts and the hard drive cannot even start up. So what's the verdict on this power supply? Let's ask our friend Senator Vreenak.
It's a fake.
Hey everyone, thanks for listening to me talk about this for several minutes. I do hope you share this material with your friends, especially if you know that your friends or colleagues are looking at these power supplies online and they just can't resist the great deals that they see through all these online sellers. If the price is too good to be true, then there's a really good chance that you're getting one of these two supplies that's pretty much fake in my opinion. For reference, I spent about a little over $3 on this supply and I did get my money back because I caught the problem before the warranty or the eBay return period expired. This one, on the other hand, it just failed several months after I purchased it, so I had no recourse in it. And I wish I had done a bit more analysis before I actually started using it. So what can we do to avoid buying these things to begin with? Well, that's the really hard part. You can try to buy strictly from the country that you're in and avoiding places like China, but in the United States, that's really difficult because often these companies that are selling these imposter supplies have warehouses in the United States, and they'll ship directly from those warehouses and advertise as they're being U.S. sellers or U.S. companies. In fact, it's just the same goods being moved across the borders in advance. So that might not always be a great strategy. Personally, what I'm going to try and do is to study the reviews to see if there's anyone who's done testing on these. And unfortunately, that means somebody has had to have bitten the bullet and, taken one for the team, so to speak. Ideally, we would be in a world where this would not happen and we would have trust in all the products we buy, but unfortunately, that's not the world we live in today. And on that note, stay vigilant, keep an eye out for fake products. Thanks for watching, and I hope to see you back soon.